Now I'm going to continue with questions 3 and 4 on your paper now. Question 3 is a multi-part question on the Leaving Cert every year. It kind of dips into everything you've done so far. Can I ask you to identify the parts that you presently could not answer? That would be important. Most of them you should be able to answer. I wouldn't take from the fact that the odd one will escape you, or you haven't it revised, or you're not familiar with it, and put an asterisk on it with the idea that will need to be followed up, okay? But you're asked in this case to answer 9 questions. I insisted on you answering any 8 correctly, and the marks I gave for that were 8 6 48, and you got a bonus 1 mark for each of the first 2 you got right. Okay, so I gave marks to the best 8. And it's important that now we'll diverse a lot of things here. We'll be crossing now in relation to stuff you've done already, but it's very good revision, and I sincerely hope that you're working okay with that. All right, now this is question 3, part A. What is the percentage by mass of nitrogen in ammonium nitrate? Now that could be difficult enough if they hadn't given you the formula, but they gave you the formula. NH4 NO3 is ammonium nitrate. Now in defense of the system, they generally will give you the molecular formula for any compound in which a calculation is dependent on it. Now I'm saying that to you from the point of view that I hope you'd at least be aware that, you know, when you're going through something like this, if it's a very obvious formula like sodium chloride or something, I think they might expect you to know that, you know, so just be aware of that generally you're given them, and that will be the case. The percentage by mass of nitrogen, and so the percentage nitrogen is equal to the mass of nitrogen over the mass of the compound multiplied by 100. Okay, now be careful, won't you? The mass of nitrogen is 14, okay, if you went looking for this, 14. So if I put 14 in there, the compound, you work out the relative molecular mass for it, it's 80, and multiply by 100, and you realize, don't you, that that's not correct, because there are 2 nitrogens in that. Okay, be careful. Very common mistake now. Very common mistake. Okay, will you be careful, please? That's 28. Okay, and your answer came out to be 35%. 35%, okay, nitrogen. Now I'd like to think you'd write the formula, that you wouldn't just be doing a calculation or coming up with an answer. I don't like to tell you get marks for the correct answer, because I think, you know, it's not the best thing to be doing, but you will. Okay, but please be careful. That's the answer, then 35% nitrogen. Next. On what principle is the analytical technique mass spectrometry based? Now, that's a bit of instrumentation. There are 5 instruments on your syllabus, and in due course you'll get around to studying them all as the 5 separate units. They're complex instruments used by chemists in everyday life, and I think you're expected to be familiar with the principle on which they work, the processes involved in using them, and at least one everyday use of such an instrument, right? And in this case they've asked you for the principle, and the principle is very simple, that when you pass ions of different mass through a magnetic field, the heavier ones bend less than the lighter ones. Okay, or you might say that particles can be separated based on their relative masses when they pass through a magnetic field. Now, if you haven't that done, I understand that, or if you haven't done for a while, it can be a bit vague with you, but you will need to have principle, processes, and a use of each, and that's all they wanted there, okay? So separation based on mass is what they're looking for there. What is the flame color for for copper, excuse me. What is the flame color for copper? There are 6 of these ions on your course, and they're practicals. You're expecting all the colours. I'm sorry now, but that's rote learning, I have to say to you. There's very little of it in the course, but you'd have to know the colours. And in the case of copper, you either know or you don't. It's a green-blue colour. You'd have to mention both green and blue. There's a reason for that, because there's another ion on your course, barium, which is green. So green-blue, okay, is what you'll be saying there, or blue-green, one or the other, right? What term, define the term standardized. Standardized, we've just been doing volumetric analysis, and it relates to that. This is a solution of known concentration, and that would have got you all bar 1 mark. They'd have held back 1 mark there, okay? A standard solution is a solution of known concentration. You're asked to explain the term standardized, and you say this is a solution whose concentration is known as a result of doing a titration, okay? Because it said standardized as a result of doing a titration. Very good. A 50 centimeter cube can of beer contains 21.5 centimeters cubed of ethanol. Calculate the percentage alcohol, that is the concentration of alcohol in percent WV. Okay, so you have in this particular instance got, I just write the figure for you, you have 21.5 centimeters cubed in 500. Okay, in 500 centimeters cubed. So if you divide by 500, you get the amount in 1 centimeter cubed, and you want percent WV, which is in 100. Or divide that by divide that by 5 if you like. You get 4.3 over 100. Okay, and it's 4.3% VV. Okay, now the way it's worded could be a bit awkward there. Will you be careful with it, please? They gave you the centimeters cubed in a 500 centimeter cube can. And they've asked you for the percent VV. Do you know that percent VV is centimeters cubed per 100 centimeters cubed? Okay, that's what VV means, and that's what you really were expected to know. So if you knew the number of centimeters cubed per 500, getting the per 100 then would be quite easy, wouldn't it? That would be what's involved there, nothing more than that. That's fine, that's that one. Good. The boiling points of hydrogen and oxygen are 20 and 90 Kelvin respectively. Account for the higher boiling point of oxygen. There's hydrogen, if I could just draw a model of it for a moment, and there's oxygen, if I was to draw a model of it for a moment. Now I'm just giving you the idea of a relative thing, okay? That's much heavier than that, okay? It's molecular mass, okay? Its MR would be heavier, okay? That one would be 2, and that one would be 32. Will you keep that in mind? Because it's much heavier, then its boiling point would be harder to gasify it. Not a great answer, but it's a relevant answer, okay? Of course, what they want from you there is to know they are both non-polar molecules. They're both non-polar, so they both have van der Waals forces. They're the intermolecular bonds. And van der Waals force, I don't want to get into it here now because I'm only revising the paper and I'm not getting into the theme itself. But basically, you get a temporary dipole in a non-polar molecule. You get, because the electrons are running around all the time, at any instant in time, they're not all located exactly in the middle. And consequently, you get a temporary dipole, and the dipole on that one would be smaller than the dipole on that because that's a bigger molecule. They'd be further apart. Okay, and that's effectively it. All you're going to say is the van der Waals forces occur between both of these molecules because they're both non-polar, but the van der Waals forces are stronger for oxygen than they are for hydrogen. Now, I very much appreciate that that's not an explanation, but the section needs to be revised, and that's very important that you're aware of that. Okay, that's what they were looking for there. Now, remember, they're short questions, and the technique in this is to get to the point. And sometimes one question is a bit longer than others because there's a narrative involved or a procedure involved, and another one, a colour is enough, like green, blue, and get over it and get on with it, okay? Sometimes you have to compensate, you have to internally compensate in the question, where a short question gets the same marks as a long question, but they're within the one question, so you might have to write a passage, a paragraph in one answer, and a colour or a word would be enough in another one. And that's where you compensate with your time then, very important. How many atoms are present in 560 centimeters cubed of ammonia at STP? 560 centimeters cubed of ammonia at STP. Okay, you obviously you're trying to work out, in this particular instance, how many atoms. So you must get how many molecules first. You must divide that's a volume, you must divide it by STP, it said. STP divided by 22.4. Divided by 22.4. You wouldn't do that, would you? You can't divide litres, okay? You divide by 22400 to get moles. Will you keep in mind anyway, please, that what you're going to get there is 0.025 moles of ammonia is NH3. NH3. They did not give you the formula for ammonia. Will you be careful, please? Okay? And so you multiply by Avogadro's number, and that will give you molecules. 1.5 by 10 to the power of 22. 22 molecules of ammonia, NH3, and you must now make a statement. I have to keep reading the question. How many atoms? Yes, how many atoms? So every molecule has 4 atoms. So you have to multiply by 4, and that's going to be 6.0 by 10 to the power of 22 atoms. And one of the few areas where you don't have to tag it because the atoms could be nitrogen or hydrogen, but that's what they wanted, nothing more than that. Next part, explain the term half-life. You've done that early on in atomic structure 1. Yeah, wouldn't you? Half-life refers to a radioactive substance. and it is the time interval in which half the radioactive nuclei will decay. Okay, that's basically it. I know, without getting into the technicalities on it, radioactive nuclei are unstable and they disintegrate, and there's a rate at which they disintegrate, and the half-life indicates how long it will take for half the present number of nuclei to decay. Okay, and that's effectively what they want from you, nothing more than that. Remember, it's a short question now, so you wouldn't be qualifying that any further. Describe a simple test for the polarity of a liquid. Now, a lot of you use solubility here. You said if I poured it into water and it did not dissolve, it would be non-polar. That's fine, but it's a bit messy, I think. But it's fine, as long as you state clearly that if it dissolves, it is polar because like dissolves like, and if it does not dissolve, it is non-polar. You'd have to state that, okay? Not just saying, see if it dissolves. That wouldn't do. Okay, you'd have to do better than that. I prefer the one with the rod, okay? That you take a stream of water coming from a burette would be grand, and take a charged rod. If you took your biro and you rubbed it in your hair, it would become charged, and you bring it near the flowing water, you'll find you will deflect. Okay, if you brought in a charged rod there, you'll find it would deflect. It would bend away, right? It would repel. All right, that would be it. Am I right in that? I'm not. Okay, you know, it would attract, yeah? That's okay? Okay, as long as you kind of accept that that's what's going to happen. It will come towards it, yeah? Are you okay? And by the way, if you brought a negative rod, it would do it as well, because the water would turn around. Water is polar. It has a plus and a minus end to it. And so the opposite ends come around to this and it's attracted. So you can pull it towards it, okay? If you put a negative rod in there, it will still come towards it, because the molecule will turn around. There's a water molecule, okay, in this case, H and H, that'll be delta minus, and that'll be delta plus and delta plus. Now, you don't need to give this in this question, I'm just qualifying for you. The water turns around so that all the minuses are attracted to that, okay? If that was a negative rod, then it would go the other way. All the pluses would turn the other way, the molecules can turn around and it would still be attracted. That's what they'd be looking for there, but that's fine, that's okay. Right, the rod deflects it. If you poured a non-polar substance like oil into water, it would form a layer on top of it. 2 layers, okay, and that would be repulsion in its own right, okay, so you could see they'd be different that way. It's a matter of opinion, whichever one you have anyway, will you make sure you're okay with it? How many iron atoms should be consumed daily to meet the recommended daily intake of iron in the diet? They give you an amount of iron that needs to be intake every day in your diet, and they're asking you now, this is a question again on moles and all that goes with that. You have 0.014 grams of iron. How many iron atoms should be consumed daily to meet the required daily intake of iron in the diet of 0.014 grams? Okay, and so how are you going to do that? You have to convert it to moles. 0.014 divided by the AR. Go and find the AR, right? And you're working from there. In this particular instance, 56. And you'll get your value there of 0.3025. Okay, 25 moles of iron. Now I just want to say something here about that. Some people will write that as scientific notation, 2.5 by 10 to the power minus 4. I'm okay with that. I just think you have a better sense of order of magnitude for numbers that aren't very small or very big. If they're not very small or very big, then you have a sense of order of size when you use a decimal number. I'm just saying that too. It can be a sense of awareness too. Remember, moles are huge, so it's not unusual to have a small fraction of moles like that. And now, of course, you need to multiply by Avogadro's number, okay, to get that, and you're going to get 1.5 by 10 to the power of 20 atoms of iron. Okay, 1.5 by 10 to the power of 20 atoms of iron is what you want there. That's very good. And lastly, you're asked here to write the electron configuration of the aluminium ion. Now, I would like to do that with you because your method could be improved, I'd say. Not if you're having a go at this and you need to be careful now. If I had more time, I would be doing this in more detail, but I just want to give you the idea. They did give you this now, by the way. They told you that was aluminium 3+. Okay, now have you a method already? Now, I'm big into method. If you have a good method, then the question isn't going to confront you in any way. You're going to be ready for it. If they change the question, you still have a method to go with it. What do you do when you get that? Aluminium is the atom. Okay, I'm looking it up here just to check everything is okay, and it's number 13. So there are 13, that's the atomic number, so there are 13 electrons in that. If there are 13 electrons in that, there are only 10 electrons in that. And so, using the Aufbau principle, we assign the electrons to the energy sublevels. 1s2, 2s2, 2p6, and you're finished. You're finished, okay? Now, if you get that in the exam, you get 0, as in no marks. And why is that? Because that happens to be the configuration for element number 10, which is neon. You would have to put a square bracket around it and a 3+. Now, that's very important. It's a very common mistake. I'm saying that again to you now. Leave out the brackets, you have the wrong answer. Without the brackets, it's not an ion, it's an atom. And what atom has 10 electrons? The answer is neon. So be careful there, won't you, with that? That's very, very important that you're dealing with it like that. It creates all sorts of issues, and you have to be sure you're putting them through like that, okay? So that's the... Now, that happens to be the Aufbau principle, their energy sublevels. Now, Pauli and Hund and then expanded that further to put the electrons into orbitals. And consequently, the expanded version of that then would be 1s2, 2s2, 2px, 2py, 2pz, 2, 2, and 2. Okay, now they're in orbitals. An orbital can only have 2 electrons. An orbital can only hold 2 electrons. So you have a lot more orbitals than you have energy levels. Now, I suspect I'm not being helpful here. I'm probably annoying you here now because this is a bit vague with you. But that is orbitals. And by the way, if you wrote that, you get nothing. Don't forget your bracket and don't forget your 3+. Now, that technically is the correct answer. That technically is the correct answer. I'd have allowed something for that, I'm telling you now. But that's the expanded version, and they could well have asked you there, they didn't ask you, but they could well have asked you, how many energy sublevels are used in this? And the answer is 1, 2, 3. And how many orbitals are used in this? The answer is 1, 2, 3, 4, 5. So I would always recommend that you write the configuration twice. Okay, that you write the short version first and then you expand it. Now, the error rate here was fairly bad. Okay, I'm telling you now, a lot of you are messing this up. Will you go back on that, please, and make sure it's okay? That's question 3 then dealt with, okay? And I would like to think that that's a cross-section of things, and we have to try and work on that, okay? Let me just break the unit there for a moment again now for you.